What is mass? Duality. Is the duality a wave plus particle or a wave or particle? I've got some data which shows you which. To prevent you losing your way, here's the path we will be taking. The photonic wave group, uncertainty, free particle dynamics from Newton to Einstein, what is mass in 5 dimensions, and double duality in zone axis diffraction with resonant responses. Here's the quantum, based on Maxwell's equations, electric vector vertically, magnetic vector horizontally, out of phase by 90 degrees, and 2 velocities, a group velocity for the normal distribution, and a phase velocity for Euler's wave. The uncertainty of this wave is the full width half maximum, or for simplicity, the full width divided by E. And here it is. dt is 2 sigma over omega primed. If you Fourier transform of a Gaussian is Gaussian, and the uncertainty in angular frequency is for omega over sigma. The dual uncertainty is 8. This is 16 times larger than Heisenberg's limits, whatever they are, and space similarly. Here's some experimental data from X-ray lithography. The critical condition is derived from Cornu spiral, and this one is 4 times greater than Heisenberg's limit. The limit depends on the details of the experimental arrangement. Now go on to discover dynamics of a particle. In Newton, momentum is mass times velocity, energy is half mv squared. In the classical wave mechanics, the velocity is the frequency times the wavelength, which is the same as the angular frequency divided by the wave vector. And this is interesting because if you substitute this equation into this, you find that momentum is proportional to lambda. That's the opposite of what de Broglie found. And what's the reason? Because this frequency depends on phase velocity, and this frequency this velocity depends on group velocity. We move on to Einstein, E equals mc squared, which divides into momentum and rest mass. Include Planck's law and translate, we find in dispersion dynamics, omega squared is k squared plus m squared, including some constants. Differentiate and we find a very important result. Omega over k multiplied by d omega by dk is equal to c squared. What's omega over k? We had that before, that's the phase velocity. And d omega by dk, we're going to find that's the group velocity. Notice, it's equal to c squared over p. Notice one more thing, that if we rearrange this formula, m is equal to 2 functions, a conservative function, which describes a particle, and a interfering function, which describes a wave. Is Newton dynamic wrong? No. We will now consider how to relativize Newton dynamic. E equals rest mass, rest energy, and these equations we've seen before. If we write P over m0, we get this equation in Newton's mechanics. and how do we translate to Einstein's mechanics? We'll see that in a moment. But in Einstein's mechanics, the group velocity is again equal to E pc squared over E if we replace Newton's rest mass energy with Einstein's relativistic energy. And notice again that we find that the group velocity in Einstein's dynamics and Newton's dynamics is equal to d omega by dk. Illustrate this physically. Think of a piano tuner, one tune out of phase, out of tone, and consider the tuner hears two waves which interfere, and they produce a carrier wave which beats, and the frequency of the carrier wave is omega over k, as we saw it before, and the frequency of the beats is d omega by dk. When we integrate this over the normal distribution, we find that the group velocity is d omega by dk, as we saw it before. So this reinforces physically the equation we derived. To illustrate, here's the rest mass, which is constant in Newton's mechanics, but which increases in Einstein's mechanics. Here's Newton's velocity, group velocity, which tends to c in Einstein's mechanics. And here's the phase velocity faster than c both from Newton to Einstein. We're now going to examine this in five-dimensional displays so that we can analyze mass. Start with relativity, and notice the 5 dimensions. P is a vector can be described in Cartesian axes, 3 dimensions. E and M are scalars, and we treat them as undifferentiated spheres and constrain them by being in the same plane as P. And then we can draw some conclusions. M is normal to P. We have a Pythagorean triangle here, and we constrain E and M to being in the same plane as P. And when we do this, we can discover several properties of the electron or the positron. But I'll not go into that here, it's described elsewhere. What we're interested in is to describe mass, both rest mass and relativistic mass, which we displayed before. And what you can derive from these equations, notice we have a new term, theta, which we can use to analyze the data. And what we find is that rest mass depends on internal motion E0 in the wave, independent of both P and Vg. The increase of M with respect to M0, M divided by M0, depends on the group velocity g and not on the phase velocity Vp. So the relativistic increase in mass with k depends on Vg, not Vp. And this leads you to understand that point particles and probabilism must be mathematics. The phase velocity is produces rest mass, and the group velocity produces the relativistic difference. The physical interpretation of the quantum with resonance response is supported by the effects of the Log-Lin metric, which I'm going to describe. And references to this work are given on this page. Press pause to read them, and notice that the Log-Lin metric is registered by the Smithsonian SAO Astrophysics Data System. The Log-Lin metric. Crystals are easy. We have a periodic probe, a periodic crystal, a periodic diffraction pattern, a Baselag's law, Bragg's law, n equals 0, 1, 2, 3, 4, 5, 6. Quasi-crystals are completely different. Periodic probe, hierarchic structure, geometric diffraction pattern. 0, 1 over tau, 1, tau, tau squared. It's in geometric series and it's irrational. Tau to the m lambda is equal to 2 t primed sine theta primed. Tau is irrational. N was integral. The structure has principal axes, which are displayed in the stereogram, and normal to the principal axes are the diffraction planes. They are all three-dimensional, geometric, simple, complete, and irrational. And this is the diffraction we get. The previous pattern we saw was for a parallel beam. Here we narrow the beam down to a point probe on the specimen, and we find a very strange result. First of all, we find the same geometric pattern we saw, only each spot that we saw before is now expanded into a circle. And though these spots are in geometric series, these circles are in linear series. 1 over 6, 6 at 1. Points 1 over 6, 0.6 and 1. So they're in geometric series, which is not Bragg diffraction. And we understand how this occurs by means of what's called the structure factor method. But how, you must ask, does a single atom, for example, a single photon, for example, diffract in two ways, one geometric and one linear? We're able to show that the geometric pattern occurs by a stretching of the blue crystalline regular periodic diffraction pattern. It stretches by the Log-Lin metric and produces a quasi-Bragg pattern, which is commensurate with a geometric lattice, both long range and short range. And you can notice some extra features. Count the number of cycles between these. 1, 2, 3, 5, 8, 13, 20. This is the Fibonacci sequence. We have here a diffraction which is not only dual, it's double dual. It's not only a particle in a wave, but it's a particle in a wave diffracts in both linear series and geometric series at the same time. And we draw some conclusions. In double duality, we have a wave and a particle, logarithmic and linear, natural and irrational, the dual resonance responses of a quantum wave group. If it's a particle and a wave.